Have you ever been puzzled by the vector equation of a line? How does it connect to the Cartesian equation? Why do we even need it? You're in luck. Get your beverage of choice and relax while we explain what this is all about. Let's start with a little review of the Cartesian equation logic. We assign each x value its corresponding y, creating coordinates of a point which we can plot in a Cartesian plane. The information contained in the equation is the gradient and the y-intercept. Speaking of gradient, a quick reminder. The gradient is defined as rise over run. In other words, how much we move vertically compared to horizontally. Keep this in mind moving forward. Now let's look at how the vector equation would be created for the same line. We will use the same two pieces of information, a point on the line and its direction defined by the gradient. First, from the origin to a known point P, we can create a position vector which is usually denoted A, in our case 0, 1. This places us on the line. Now we just need to follow its direction. Going back to the illustration of gradient, note that the rise and run match the y and x components of a vector parallel to the line, what we call the direction vector. B in the general form and 3, 2 in our case. Anchoring this at the end of our position vector, the addition gives the position vector of a second point on the line. This is great, but we probably want a bit more. What if we wanted to reach other points, say the one in the middle of the ones we already have? We could do this with a shorter vector, but do we have one? The answer is yes. This is where the parameter lambda comes into play. Recall that multiplying a vector by a scalar just stretches or contracts the vector it's applied to. To reach the point on the screen, we just need to contract the direction vector by a factor of 0.5. In this way, we can reach any other point on the line by using different values for the parameter lambda. For instance, if we want to reach a point on the other side, we use negative values of the parameter, which takes us in the opposite direction. If we draw a point at every place the tip of the arrow ends up in, we see the line finally appear. The vector r is not parallel to the line in most cases. We say it represents the line since for any value of lambda, r will correspond to the position vector of a point on the line. With this in mind, let's clarify a second common point of confusion, the non-uniqueness of the vector equation of a line. Given 2 points, if you were asked to find the Cartesian equation, you would likely end up with. However, this is as much about conventions as it is about math. You're used to seeing Cartesian equations of lines on gradient intercept form, but we could just as well write it in these other ways. In a similar manner, the following two would be perfectly valid vector equations for the same line. As long as a vector goes to a point on the line when anchored at the origin, it can be used as position vector, while any vector parallel to the line can be used as direction vector. The only thing to watch out for is that the parameter would be different for each equation if we wanted to reach a specific point, P in this case, since the amount of stretch we need to give to our direction vectors would be different. But there's no convention as to what to pick as position or direction vectors, so don't be surprised if seemingly different equations represent the same line. This is all good, but what's the point of adding a new representation and going to all this effort to understand it? The Cartesian equation seems good enough. Now let's begin with a different question. Can you think of what the Cartesian equation of a line in 3D is? It's not at all obvious. On the other hand, the vector equation is more than just similar. It is identical and the logic is the same. Let's start with 2 points in space and a line between them. We create a position vector from the origin to one of the points and a vector parallel to the line, which we add to get a position vector of a point on the line. We can then stretch or contract the direction vector to get the position of any point on the line, just like in the two-dimensional case. And so the equation is the same, the only difference being that our vectors will have 3 components as opposed to 2. While it may take a bit of effort to understand the idea of the vector equation, It pays off by not needing to introduce anything new for higher dimensions, in addition to allowing us to use vector tools. Indeed, the logic works if we wanted to place a line in 5D, or 7D, or even 1729D. The equation of a line will be R equals A plus lambda B. This is pretty common in math as a whole. We try to develop tools and theorems to simplify work further ahead, not only specific cases. So next time you encounter a new method to do something we could already do, keep this in mind. Alright, that's it for today. See you in our next video. This video is brought to you by Lighthouse Global, your personal online tutoring for IB, college applications, and school subjects.